Asalamualaikum and good morning. My name is Eleshaa Binti Chandrasekaran. My matrix number is 213150. Today we're going to represent ordinary differential equation in Kircchoff's second law. Today I'm going to represent the introduction of Kircchoff's second law, which is related to electrical network. What is electrical network? An electrical network is a system that connects electrical components such as battery, resistor, inductors, capacitors, switch, and transistor, or a model of such a system voltage source, current source, resistance, inductance, and capacitance. Next, the history of Kircchoff law. So when does this Kircchoff law start? The history of Kircchoff law is starting from Gustav Kircchoff, a German physicist who lived from March 12, 1824 to October 17, 1887, that discovered Kircchoff rules, which defines current and voltage in electrical circuits, are his most famous invention. Okay. Kircchoff made a variety of other important contributions to physics, including work to spectroscopy and black body radiation. In addition to his law, investigated and discovered two principal related electrical circuits with lumped electrical elements, which is Kircchoff's first law and Kircchoff's second law, were defined in 1845 after he pursued the notation of Ohm's law and Maxwell's law. Okay. So we're not going to talk about the first law, we're going to talk about the second law that he discovered. Follows the law of conservation of energy as the following assertion demonstrated the amount of charge gained is equal to the amount of energy lost in a closed loop. The resistors in this closed circuit are to blame for the energy loss. Furthermore, the total voltage loss across the closed circuit should be zero. For example, in figure 1 below, it can be expressed mathematically as summation of V equals to 0. Figure 1 is this one. As you can see, the sum of all voltage drop around the loop is equal to 0. So VAB, VBC plus VCD plus VDA is equal to 0. Okay, the principle of Kircchoff's second law is a total charge of current entering the circuit equals total charge or current leaving the circuit. Says this law, this law is based on the conservation of charge principle, which stated that charges cannot be created nor discharged. Okay, Kircchoff current law terminology when worked with KCL and KVL, words with node or junction, loop, mesh, and path are employed. Let's clarify these terms. As you can see on the slides, a single dot means a node or junction in the circuit. A junction means different current paths in the circuit. Branch means two nodes when joined in form of branch. Loops, it means that closed path in a circuit in which electronic device such as a resistor and capacitor. As you can see, example of loops in the diagram. Dots means like this. Like this is dots. Junction is this one junction, this is junction, and this is all a junction. And also this is considered as a branch, one branch and a two branch. And this is also a loop. A loop you can determine however you want to determine the loops. So next we're going to talk about the potential drop across the element. Will be considered as negative when the direction of flowing current in the loops is the same as the direction in which we are traveling. Basically, this is talking about how you indicate the positive and negative sign in the law. First is if the current flowing in the loop is flowing in the opposite direction as the transversing direction, the potential drop across the electric component will be positive. Next is if the negative terminal of the battery is encountered first in the transversing direction, indicating that the battery is generate current in the direction of our traveling, the battery potential is assumed to be positive. If we come across the positive terminal of the battery first, indicating that the battery is generating current in the opposite direction of our traveling, the battery potential is considered as negative. One with there are three different, because the first one, the A is two closed loops with a power supply. As you can see, there is a battery, and the second one is without power supply, assume current. This one is what we call Kircchoff law. This is what we are assuming. Next is without a power supply with an actual current flow. So and assumed current flow has been introduced in figure 3b. As you can see, in this case, the schematic has been updated. It includes additional wires to indicate that it is part of a big circuit. This clarifies that because there is no DC supply in the situation, current must enter and exit the loop. Next is figure 3c. Assume that V2 equals to V3 equals to V4 equals to 2V. So V1 must be equal to negative 6V. This indicated by the current flowing through the resistor corresponding to V1. Okay, the last equation here, this is considered a simple current. We have EMF of E1 and E2, while resistance is R1 and R2, and the current is I1 and I2. The equation should be this one, but I'm showing you below here. So basically what I'm talking about here is the EMF, and if it's related to power, current and resistance, this is the equation. That's all for me. Thank you.
Hi, Asalamualaikum warahmatullahi wabarakatuh. I am Nabilah Khairani, Binti Saleh. My matrix number is 212023. Are going to represent in our presentation today that explain about ODE in the Kircchoff voltage law, which is Kircchoff second law. So I'll be explaining on application and examples. So enjoy.
First, let us see the differences between the first law, Kircchoff current law. First of all, at the first half, we know that the first law, KCL, explained about the sum of inflowing current at any point in the circuit must equal to the outflowing current. The example show a parallel circuit that has different value of inflowing resistance and current. If we separated the negative part, or we should call negative rail at Y8, 7, 6, and 5, and positive rail at 1, 2, 3, and 4, we can see that each opposite side of wire has equal value of current. This happens when I total move. For example, from the root 5 to 4 through resistance R3, which produces current R3, and current total that move from node 6 to 3 through resistor R2, which produces IR2, made at rate node 3 to 2 equals to IR2 plus IR3, which is same as the node 7 to 6. To summarize, KCL is an algebraic total of all currents entering and departing a node must equal to 0. This can be proven by the fact that if the sign or polarity, which indicates whether the enter sign given as plus or exits minus a node, then the total of all current is equal to 0. Now, the figure shows 4 voltmeter at 1 was connected with black test lead and red at 2. The voltmeter E221 is equal to plus 45 voltage. Now to clear things up, if the term stated as E221 means that the first point is at 2 and second is at 1. Let's say the red lead is the point ahead and black is the point behind. So the notation will be as the figure shows. Now that the principle is becoming more clear, the most important things is the polarity. As what has been said, in KVL, the sum of voltage drop will equal to 0. By taking the polarity into account, the total voltage equals to 0. Now, let's disregard the path of which the voltage moves. Now that if the voltage moves the opposite direction with the polarities, the sum will still be equal to 0. Now, let's look into a much more complex circuit. This is where ODE is required for us to obtain the voltage value. Now, based on the figure shows, we can come up with the following equation, where T is the constant electromotive force equal to the voltage flow through the circuit IR. In addition, the differentiation of inductance. The equation can be derived if only the circuit is in closed loop, given E0 equal to constant, into following equation. Now based on the following graph, as t approaches infinity, the last term approaches 0, and current t approaches the limiting value of E0 over resistance. Let's say the current from the previous graph is known as the angle, and the t over s as the function of omega inductance over resistance by considering Et equal to E0 sine omega t combined with the equation yields the equation above. Integrating it by parts given as the second terms, and this can be further derived as the last equation. As t approaches infinity, the exponential terms tends to approach 0. This means that after a sufficiently long length of time, the current T achieve almost harmonic oscillations. Now let's take a look at the example. A series RL circuit with resistance 50 ohm and inductance with 10 H has a constant voltage of V equals to 100 voltage applied at T equal to 0 by the closing of a switch. First, we will have to equate for current by using the equation, and we will lead to in bracket 1 minus exponential power of minus 5t. Now we can apply it into the graph that shows the current at time t. Second step is to find at t equal to 0.5 second. So we can apply the second into the equation that we used before, which will equals to 1.8358. The next step is to have the expression for inductance EL. We can use the equation E equal to IR by applying the answer before. To obtain the value of inductance is to differentiate the inductance to T. So now let's equate the time where R resistance is equal to L inductance. So the answer will be negative 0.69315. So we can have the time which over with a negative 5 is equal to 0.139 second. By substituting the value into the equation, R equal to L, we will have 50 voltage. 50 volt, I mean. So the graph indicates that resistance is equal to 100 in bracket 1 minus exponential of the power negative 50 in green line, while inductance is equal to 100 exponential with the power of negative 50 in gray line. Now to find the time constant is by using the equation below that indicates using T. So rather than using the above method at 1, so the previous method could also lead to this answer. The required differential equation is as shown. To solve the equation is by taking into account the mathematical solution, which is shown. Now, since the current at time 0 is equal to 0, then K is equal to minus 2. So it is proven that current at T is equal to 2 in bracket 1 minus e to the power of negative 5t. So we have reached at the end of our presentation today. I hope you guys enjoy with our presentation and have the understanding a bit about ODE, ordinary differential equation, that has its own contributions towards our daily life, especially in this topic, which is Kircchoff's second law. So I do hope we can meet again. Thank you.